It's the purpose of this video to simplify many of the complex problems which occur in the MIG welding industry today. Today's welder has got many variables that have to be adjusted and balanced. For example, is he using the correct size wire and the right type of wire? Should he be possibly using a flux cord, or should it be a MIG wire? And then what about the voltage and the amperage, the wire feed speed? This has to be balanced very carefully to get a spatter-free weld. What about the gas? And then technique. These are all questions which require answers. And it's the purpose of this video film to provide simple, no-nonsense, straightforward solutions to these problems. You know, selecting a power source today is a little different from what it was 10 years ago. The range of size of power sources has changed dramatically as we've gone, and particularly in North America, to thinner materials. The amperage output requirements is much less now than what it was 10 years ago. Let's look at some of the features that you might want to consider when you're selecting a power source. Some of the units on the market offer the two slope outputs, a steep slope and a flat slope. What does slope mean exactly? Well, in this particular machine, the steep slope provides control during the short circuit. It doesn't allow the current to be too high each time the wire short circuits. So if you're welding thin metals, having a steep slope output provides a little bit better control. And then when you go to spray transfer, you might possibly want to weld 3/16 half an inch steel. Then you would have the flat slope output. The flat slope output actually allows more current if a wire does short circuit, so that the power source can respond more quickly to the changes during a weld. Now, a lot of machines basically may not have these two outlets on here, but they will have an output which is somewhere in between the steep and the flat. Again, some machines have the inductance. What is inductance? Inductance is beneficial, again, in short circuit applications. It kind of slows the current down each time a short circuit takes place, so we don't have this instantaneous response and surge and explosion. In other words, it's really beneficial for cutting down on spatter, and because the arc is on time a little bit longer, the short circuit welds may be a little bit more fluid and therefore look a little bit better. When you look at a power source today, you can simply look to see that the power cable is attached to the positive side, and that power lead should in actual fact find a connection up on the wire feeder. It's usually connected to the torch block. The easy way is simply just to check that the ground cable is attached to the negative side. I've always remembered it the old simple method that reverse electrode positive stands for the Republican Party, REP, reverse electrode positive.
Applications. If welding up to 3/16 of an inch, a 150 to 200 amp single-phase power source is sufficient. 035 wire is the most practical choice. A 250 to 300 amp power source is practical on metals up to 1/2 inch. This is typically a 3-phase power source. This is ideal for 035 MIG wires and 045 flux cord wires. A practical power source for today's fabricator is a 400 to 450 amp three-phase unit, which has a wide range of applications. Ideal for 035 to 045 MIG wires and 045 to 1/16 flux cord wires.
You know, stops and starts in MIG welding are responsible for about 90% of all the defects that occur. And the greatest influence on stops and starts is how you select your wire feeder. Let's look at some of the main features that should be given consideration in selecting a good wire feed system for MIG welding.
Consider the following features when selecting a wire feeder. The drive motor is the heart of the unit. A permanent magnet motor runs much cooler than a shunt motor. A permanent magnet motor also responds much faster for improved stops and starts. Gas coverage is critical at the weld stops and starts. A practical wire feeder feature would be a pre- and post-gas flow control to ensure gas coverage. Also a gas purge switch to eliminate air from the gun. Burn back control eliminates the need to keep trimming the wire for the correct stick-out length. Correct stick-out ensures minimum spatter at the weld starts. For consistent amperage, a digital wire feed speed readout enables the operator to obtain consistent results. An important safety feature is a cold feed control, which feeds wire through the torch without connecting the current.
You know, selecting a MIG gun can be critical if you're a high production shop. There is so much time lost today in production welding because of the wrong type of nozzle. Maybe somebody should have ordered a heavy-duty nozzle. And what about the contact tip? Is it a short one? Is it a long one? Does it suit the specific application? And of course the gun itself. Is it designed for the duty cycle in which you weld? Can it take the spray transfer? Is it designed for it? There are many factors which should be given consideration in selecting a gun.
MIG gun selection. With power supplies using less than 200 amps, use a 200 amp gun. With argon mixes using up to 300 amps with less than 60% arc-on time, use an air-cooled 400 amp gun. With argon mixes using up to 400 amps with low arc-on times, use a 600 amp air-cooled gun. When welding with argon mixes above 200 amps at an arc-on time over 60%, a water-cooled gun is recommended. When using argon mixes above 200 amps and an arc-on time over 50%, to extend the nozzle life, use a heavy-duty gas nozzle.
We've talked a lot so far about short-circuiting and spray arc. What is exactly short-circuit and spray transfer? These are two different modes of transfer which really make MIG welding unique. As a matter of fact, no other welding process provides two distinctly different forms of weld metal transfer. Now with the short circuiting, considered a low amperage mode of transfer in which the wire short circuits generally up to about 120 times per second. Then we have the high amperage spray type transfer in which the wire doesn't short circuit and it's generally over 200 amps. Deep penetration, high deposition. So you see we have one mode of transfer short circuiting, ideal for sheet metal applications, and then we have the other mode, spray transfer, ideal for thicker plate, generally over 1/8 for 3 millimeter plate. When we understand how to set the parameters for these two important modes of transfer, then we truly understand the MIG process. You know, with MIG welding, it's really the amps that melt the wire. And we have to get amps out of the power source. Now, the voltage will push the amps out, but the bottom line is we have to have a conductor, something for the amps to travel along. Now, if we have no wire coming out of the gun, then we can't draw amps out of the power source. The faster that the wire is fed through the torch, then the more amperage or current it can draw from the power source. Now you've got to remember that the current actually is fed into the wire just about 1/4 of an inch from the end of the contact tip. So it hasn't got far to travel. And typically for short circuit welding, we have to feed the wire basically at about a rate of 100 to 200 inches a minute. And this will draw from a power source 50 to about 150 amps, which covers the range for short circuit welding for 030 and 035 wire.
An increase in wire feed speed results in an increase in current drawn from the power source at a given voltage setting. The wire feed speed range for short circuit transfer is approximately 70 to 300 inches per minute. At 70 to 300 inches per minute, the current drawn from the power source will be 50 to 175 amps. This is the required current for short circuit transfer. A simple setting for short circuit transfer. Set the wire feed knob at the 11 o'clock position. For digital feeders, set initially at 175 IPM. This applies to common wire feeders that provide a wire feed speed of 600 to 700 IPM. If an increase in wire feed speed does not provide a sufficient increase in arc energy, the next step is to increase the voltage slightly. The voltage range required for short circuit transfer is 13 to 23 volts. An optimum starting point is approximately 17 to 18 volts.
You know, so far we've talked about the basic requirements for short circuiting. Voltage in around 17, 18, wire feed around the 10, 11 o'clock position, or you could even start it off in the middle, as long as you're in the range. Let's look at some real applications with one objective in mind. We don't want spatter, and we want to do all these applications on one simple setting. Applications like, well, 10 gauge plate, vertical up. Applications like 60 thou material, fillet weld. How about a root pass in a pipe? These are basically short-circuiting applications. Remember, the simple rule is if it's less than 1/8 of an inch, or it requires vertical up or vertical down, or you're welding a gap, you simply think of short-circuiting welding. We go over to the machine. with the voltage. We adjust the voltage to strike an arc on a plate and watch the meter so we've got 17, 18 volts. With the wire feed, we simply set the wire feed in around the 10 or 11 o'clock position. And now let's look at the 1/16th application. Again, we will use the same parameters with the objective of a complete spatter, well, a spatter-free weld. As we examine this 1/16th plate, we look at the weld. We can see again, absolutely there isn't one piece of spatter on the plate. And it's really not so much welding technique as it is simply setting those parameters where they should be. It doesn't matter whether you're welding a pipe or a piece of sheet metal, you're going to use short-circuit welding. And in short-circuit welding, particularly on quality work, on code work, and on very thin sheet metals, wire stick-out becomes critical. Notice on this pipe application that the wire stick-out is approximately 3/16 of an inch. By keeping the wire stick out small like this, I can use the minimum amount of voltage, which on an application like this is usually around 17 or 18 volts. If your wire stick out, like many operators, is going to be a half an inch long due to the fact that your contact tip is now down inside the nozzle, see we have a half to 5/8 of an inch, you will need at this particular setting an extra volt or two. And having those extra 1 or 2 volts every time the wire short circuits, again, the arc becomes a little less stable. So the critical thing is, on short circuit welding, contact tip about 1/8 of an inch outside the nozzle, and the wire stick out about 3/16 of an inch from the end of the contact tip.
Short circuit wire selection. When welding continuously on sheet metal less than 045, use 030 wire. When welding on sheet metals more than 045, use an 035 wire. If using straight CO2 gas, use a high silicon wire, such as an E70S-6. When welding coated or galvanized steels, avoid the E70S6 wires. High silicon wires promote cracking. Use E70S-3.
When you select a welding gas, for short circuit welding, there are certain factors that need to be considered. if you're welding on very thin metals, less than, say, 60 thou, then it's wise to use an argon mix which doesn't have a lot of reactive gas in it. What does that mean? Well, the typical mix in the marketplace is 75 argon, 25 CO2. But if you're going to weld on 25, 30 thou materials or weld along the edge of a sheet metal, then why not use argon with we'll say 2% oxygen? Why does this benefit your application? Well, simply from a point of view that argon oxygen uses less voltage than argon CO2. For example, with argon CO2, you would require 16, 17 volts to keep a stable arc. But when you get into argon oxygen, you can work at 13 and 14 volts. Again, where should you use argon oxygen? On sheet metal, where you want to weld along the edge of a sheet metal, on sheet metal, say less than 40 thou, you will find it extremely beneficial to use 98 argon, 2% oxygen. When you're welding on an application such as this, where it's just over 1/8 of an inch and you want to put a nice bead without spatter, you obviously need more heat. Using now 75 or 80 argon and 20% CO2 is fine for an application like this. But if you constantly weld in a shop and where you're welding on sheet metals and you never go above 1/16 of an inch, then it's wise to use maybe 8 to 10% CO2. After all, you know, when you're welding sheet metals, the object is not to burn through. And if we can reduce the heat just a little bit by reducing the reactive part of the gas mix, then it makes it a little easier.
Short-circuit gas selection. Characteristically, CO2 creates a digging effect, which reduces arc stability. Utilizing CO2, the arc is hotter, influencing burn-through potential on thin metals. With CO2, the volt and amp range is very narrow, which makes it difficult for the welder to obtain optimum arc stability. Using CO2, the spatter level increases with an increase in current. CO2 promotes more surface oxides, which should be removed before painting. The material thickness, joint type, and weld position are the prime factors in considering an optimum gas mixture for short-circuit welding. On metals less than 035, argon oxygen allows the use of lower voltages, which reduces burn-through potential and minimizes damage to coatings on the opposite side of the material. Remember, the thinner the sheet metal, the less heat it requires from the welding gas. These mixtures provide the required level of arc energy with optimum arc stability. For increased arc energy, a slight increase in reactive gas improves penetration and weld fluidity. For root passes vertical down or filler passes vertical up on pipe less than 3/8 of an inch thick, use argon 15 to 25% CO2. This provides penetration and arc stability. If the pipe is thicker than 3/8 of an inch, CO2 is required for the filler pass to provide sufficient sidewall fusion. The most practical gas mix for a plant using bulk would be to set the mix at 15 to 20% CO2.
If you look at short-circuit welding, first of all, simply look at the application. If you're welding overhead or vertical up, if the plate is less than 1/8 of an inch, if there's a root gap or a large gap that you have to fill in, then simply think short-circuit welding. Set your wire feed around the 11 o'clock to 12 o'clock position, somewhere in the middle. When you strike an arc, make sure that your voltage is showing 17 or 18 volts. then simply increase the wire feed for more heat or decrease the wire feed very slightly for less heat. If you're welding on less than a 1/16 of an inch, set your voltage at about 16 volts and set the wire at about the 10 o'clock position. Listen to the sound of the arc. You want to hear a smooth, constant crackle. On a flatbed such as this, the majority of welds are actually done in what we call the spray transfer mode. Spray is hot. Unlike short circuiting, we are welding at much higher amperages and much higher voltages. It's a different mode of transfer. You now need the right type of protective clothing. With spray transfer, you have to protect your arms, your neck. Any skin should not be exposed to spray transfer. With spray transfer, it's the hand that does the welding. You have to have good gloves for spray, particularly as you get into the higher amperages. And for a welding shield, you need at least a number 11 shade. This then is spray transfer. It's hot, penetrates deep, and you can weld on 1/8 plate to any thickness. Unlike short circuiting, it requires, again, a careful balance between the voltage and the current. On many applications, this may be too hot, so we back it down to a more form of globular transfer.
Determining when to set the power source for spray transfer is simple. If the steel is over 1/8 of an inch and the welding is done in the flat or horizontal position, set for spray transfer.
You know, spray transfer has its own requirements. But, like short circuit welding, we can make it simple. Let's look at the fundamentals required to get spray transfer. This particular power source is a 450 amp machine. As we mentioned earlier, it has two different types of tap outputs. If your power source says flat slope and steep slope, for spray transfer, set the setting at the flat slope. Or if it just provides a low amperage and a high amperage, make sure you put it on the high amperage tap. The output of that power source is designed to give you better response on that particular tap. What about voltage? Well, the voltage range for spray is 23 to 33, and quite simply put it in the middle. Start off at about 27, 28 volts. Amperage, 045 and 035, you generally have to be just above 200 amps to get good spray. To get 200 amps, you have to feed the wire through at about 350 to, well, anywhere up to 700 inches a minute. This particular wire feed is the gear ratio is such that it provides up to 900 to 1,000 inches per minute. But typically, 90% of all wire feeders available in the marketplace are generally up to 700 inches a minute. The wire feed range, therefore, for spray transfer would be from about the 2 o'clock position, which will just bring you into 350, 400 inches a minute, all the way down to the end of the range. Again, a simple starting point for spray transfer would be set the wire feed just past the 2 o'clock position. If you have the correct voltage, when you strike an arc, your only adjustment should have to be therefore with the wire. You want more heat, you want to make the weld bigger, put in a little bit more wire. The 27 and 28 volts is right in the middle of the optimum range.
The voltage range for spray transfer is 23 to 37 volts. A stable starting point with minimum spatter would be 27 to 28 volts. This applies to 035 and 045 wire diameters. For 035 wire, a minimum of 175 amps is required. The optimum starting point would be 225 amps. To obtain 225 amps, set your wire feed speed at approximately 400 inches per minute, or the 3 o'clock position. For 045 wire size, the minimum current required for spray transfer is 220 amps. An optimum starting point would be 250 amps. To achieve this, set the wire feed speed at approximately 325 inches per minute, or the wire feed knob at the 2 to 3 o'clock position.
Can you remember where we set the contact tip for short circuit welding? Slightly outside the nozzle, keep the wire stick out short. Spray transfer is the exact opposite. We should set the contact tip slightly inside the nozzle, maybe about 1/8 of an inch down inside the nozzle. Two reasons for this. One, we need a longer stick out because we no longer short circuit. And the other reason is we want to protect the contact tip from the intense heat. The wire stick out should be 1/2 to 5/8 of an inch in length. When you put the nozzle on, make sure the contact tip is slightly recessed.
Remember, when using spray transfer, the selection of your MIG gun is critical. Use the information previously provided under MIG gun selection earlier in this tape. Improper selection will result in early torch failure and a high nozzle and contact tip failure rate, which will also influence arc stability.
In this highly competitive industry, everybody tries to find a way to save a dollar. If you use spray transfer on 1/8 to any thickness in the flat and horizontal positions, then you can save some money by selecting an 045 wire instead of an 035 wire. You know, an 035 wire in spray transfer is fed at almost a feed rate of 10 inches a second. Now with an 045 wire, the feed rate would actually be in the range of 6 inches to 8 inches. The slower the feed rate through the system, the less feed problems in general. We can also achieve the same high depositions by just increasing the current. We get very good arc stability, a slightly wider voltage coverage off the larger wire. All the economical sense is there. It costs less, it's better to use. So consider 045 wire for your next spray application. Many cases of spatter and poor welds, it's quite often just a matter of a fine adjustment on the power source.
Too high a voltage results in a quiet arc sound. The weld will be extremely fluid, producing an uncomfortable amount of heat for the welding operator. Smoke levels will rise as voltage increases. The results of too high an arc voltage are all too obvious. High volts will result in unacceptable undercut. Excessive surface oxides are also usually an indication of too high a voltage. Weld bead width increases.